Hi, we're going to get started with EDTA titrations. We're going to split this one into two lessons to make this a little bit more condensed for you to watch, just in case you need to have a break in the middle, but let's just get right into it. So today the goal is to calculate the amount of free metal present at any point during an EDTA titration. So I know the introduction to this was all about which indicators you use and which metals you can and can't target, and considerations you have to make for like blocking and things like that. All of that considered, wonderful. That's really like a practical approach to it. But now we're going to look at more of the theoretical end of things. The biggest difference, the first thing to talk about, is that instead of measuring pH at each of these points during the titration, we're going to be measuring PM. And keep in mind, of course, that the letter lowercase p is just an operator, which means negative log base 10 of whatever you're talking about. So hypothetically, it's possible to take the negative log of anything. It just only makes sense to look at pH in an aqueous-based solution since Kw is present and affects everything. But looking at these solutions, we actually get to get out of it a little bit. While there is that pH to consider, we're going to look at things like PNA, PCA, pK, which isn't really what it means anymore. But here's an example. So again, we're looking at this PM concentration over on our y-axis instead of pH. So take a look at this. You've got a lot of text on this slide. There's your caption telling you what's actually happening. For each region, it says describe the contents of the solution. So that's what we're going to do. And then we're going to take a minute to talk about how this is and isn't like what we've seen before. So in region 1, that means that the amount of EDTA we've added, because we're adding EDTA, 3 regions of an EDTA titration for the reaction of 50 milliliters of that metal ion with that EDTA, and the amount of EDTA added. So this is the idea that we've got our burette, and we've got, our flask down here, a very poorly drawn flask. Here is our metal ion. Here is our EDTA. That's the rough sketch, the rough setup. We're adding EDTA to the metal. So you have a certain metal ion, and as the reaction goes on, the amount of free metal will decrease. That they're telling you that in case that wasn't absolutely clear. So in region 1, we've got less than the total amount of EDTA added in terms of moles, in terms of volume. So what that means is that you're going to have excess metal. Here in region 2, that's our equivalence point, and here we're going to have the moles of metal are equal to the moles of EDTA added. And don't forget, we're saying EDTA as a global term for all of the forms. We're not saying Y4 minus anymore because we don't want to deal with these 6 Kas. And then in region 3, we've added extra, so that's excess EDTA. So, and that's all of those thoughts are really going to drive our approach in analyzing each of these 3 regions. The one thing I will mention is that regardless of what is in excess, the goal here is always to figure out what the metal ion concentration is, because that's what we're taking the negative log of. We're only measuring the free metal at each of these points. Obviously, there's mass balances to consider, but we're trying to not do that in terms of our graph. So how is this like an acid-base titration? And how is this not like an acid-base titration? Really having a hard time with the pen the last few days. I mean, this would be a good point for me to ask for answers from the class, but you're not here now, you're here at some later date, so I think I'm going to have to fill in the blanks here. In general, this looks like the general shape is the same. The slope appears to look like a strong acid, strong base titration, where we've got this like slow incline, sharp jump, slow incline. So it's not like we're looking for like the midpoint to find any PKs or anything like that, because, well, while there is an equilibrium with the bound EDTA, we're going to see that it's not quite that way once we get there. Ways in which it's not like. The biggest thing I noticed in how it's not like is this region 3. Notice that the leveling off PM concentration is somewhere between 15 to 16. PM values not bound to less than 14. Because since we're not using kW anymore, we're just talking about the negative log of the metal ion concentration, you can have ridiculously large or ridiculously small metal ion concentrations. So we need to break our minds of expecting to see a certain number, because the certain number that we see is actually more a function of the K prime F. So we need to do that. So for the rest of this video and the next video, we're going to be taking a look at this sample solution, 50 mil aliquot, 0.04 molar calcium, we're buffered at pH 10, we're adding 0.08 molar EDTA. I realize that at a pH of 10, you're probably precipitating your calcium ion. I don't know, man. Like, assume you've got masking agents or something. Like, just assume you got what you need to make it. We're building a hypothetical curve here anyway. You don't need to, like, ding that and nickel and dime me out of this. Just go with me. I'm trying to pick easy and reasonable numbers. To figure out the equivalence volume, we're going to do MAV equals MBVB, but I guess it should be MMVM equals MEDTA V EDTA. Because remember that at the equivalence point, it's still true that the moles are equal, so we can still use that titration equation. It's just not an acid-base based titration. Plugging in our values, we've got 0.040 molar 50.0 milliliters equals 0.0800 molar times V. And then, so here we're going to get V equals to 25.0 milliliters, and that's going to be our equivalence volume. It's great. So now we've got an idea of where our regions are. Region 0 is obviously zeros. Region 1 is 0 to 25. Exclusive. Region 2 is 25, and region 3 is everything above 25. We've got everything set up. For K prime F, just as a brief reminder, K prime F, or KF prime, can't remember which one's easier to type and easier to write. There's probably a difference between them. I kind of just write them, don't worry about it. Is alpha Y4 minus times KF. So since we're at a pH of 10, our alpha is 0.30. Since we're dealing with calcium, the KF is 10 to the 10.65, and when we multiply that, we get 1.34 times 10 to the 10th. So already this should really start to set the stage to say, I don't expect an acid-base titration, even though it looks like an acid-base titration. To calculate PM, or PCA, we have to first figure out what CA is. So for region 0, before any EDTA is added, this is pretty straightforward. The amount of calcium is equal to 0.0400 molar, negative log of 0.0400 molar equals PCA equals, I definitely forgot to calculate that. I calculated all the region 1 stuff and not this. I get a lot, 0.04, but 1 point, we're going to round 398. Like I said, this whole first region looks a little low in the PM category, and that's fine, but this isn't, obviously it's not the same graph since we're starting with 0.05 molar, but it's going to be pretty close. It's going to be between 1 and 2. But yeah, that's our starting value. So looking at region 1, because this is an EDTA metal titration, and because we've established that the formation constant is on the order of 10 to the 10th, you basically consider that a one-way reaction. As long as we're not at the equivalence point, metal plus EDTA is definitely just in a one-way process going to make your complex. So we're going to say that the dissociation is negligible. If anything, there's that tiny, but we're going to call it 0 to save ourselves a headache. Which means if we're doing it that way, that's strong acid, strong base, like I said. And in a strong acid, strong base process, we had said before that the amount of H plus or OH minus at any given volume is equal to your H plus at initial times a percent remaining. Yep, I can spell. Having a good day. Ugh. Times a dilution factor. So in this case, for this specific problem, we're going to say that our calcium ion concentration, actually I'm going to write that bigger because I'm going to write the formula and then we can make a table. So we're going to say that the calcium ion concentration at any given volume is going to be equal to our initial times, in this case, we're going to say 25 minus x. Or I guess, you know what? Instead of x, we should say v, because it's a volume. I wish the eraser... Oh, no. Oh. I'm going to write that all again. Well, no, I'm going to write this part again. It all got erased, so I'll write it up here. I'll just continue. The calcium ion at any given volume is equal to the calcium ion concentration. I've never touched that button before. 25 minus V over 25 times 50 over 50 plus V. And the reason why we're writing it this way, so this is going to be our percent remaining, and this is going to be... Ooh, I'm not even going to erase anything anymore. I'm just going to draw over it. We're going to call this our dilution factor. And remember that since like in dilution and percent remaining, as long as we're keeping our units consistent, then we don't have to convert it to liters every time. 25 minus V over 25, since 25 is the equivalence volume. So like at 5 milliliters, you will be 80% remaining, right? 20 over 25. So that's going to be our simple way to write that. And our dilution factor, the 50 is there because our initial volume here is 50 for our calcium ion solution. So for volumes of 5 and 12.5 and 20, our calcium ion concentration, and then our PCA, you can hit the pause button and do your calculations for a couple of these, or you can wait 15 seconds for me to give you the answers anyway. But I encourage you to at least go through the calculation, make sure you know what you're doing before I tell you what the answers are. Good. So here's what I got. Our calcium ion concentration is 0.0291 at 5 milliliters of EDTA added. At 12.5, we're at 0.10160. You might say it's 0.02, but don't forget that there's been a dilution there, and so we've added 12.5 milliliters. We've added our volume, increased our volume by 20%, so we decrease by 20%. That actually makes perfect sense. And then at 20, we're at 0.0571. Two zeros. I'm just realizing that, you know, if not for the dilution, you definitely could just do a lot of this in your head by the fraction remaining. And so you can kind of get a feel for if you're in the right spot. Like 0.040, that's like, if you think 40 and then 25, and so 80% of 40 and 6 makes... 6 times 8 is 40. Well, it makes sense in my head. But then these dilution factors get in the way. Anyway, this points to a PCA value of 1.536. This points to a PCA value of 1.796. And then this is 2.434. So just a couple things I'm noticing. One, the PCA values are all inherently pretty low. Two, obviously you're not going to get each one unit is a tenfold change, right? So you can look at the numbers, make sense. But as the calcium ion concentration goes down, the PCA goes up. And then three, we're 80% of the way through the titration, and our p-value is only gone up by like 1 unit. But if you kind of look back at this graph, that is consistent with what we're seeing. And again, that matches up with the strong acid, strong base methodology, where you don't really get the slope until you're at the equivalence point. So just one final thought with this, taking a look at this. I found this is figure 11-12 in the book, and a thought I wanted to leave you with is, why is it that in region 1, both of the lines are actually on top of each other? And actually, you know what? I'm going to start with this in the next video. I'm not going to give you an answer. If you want, put a comment below this, or put a comment on Classroom, wherever this actually ends up getting posted. But why is it that, take a look, all the information's there on the caption. Why is it that the two lines are actually identical in terms of the PM value? And I guess that means it would be identical regardless of what the metal is. I've never left you guys with a question before, but I kind of like it. Thanks for watching.